Okay, so in this video we're going to take a look at Lenz's law. So the first thing I want to look at is why we actually need this law. So in the previous video we met Fleming's right-hand rule, and that allows us to predict conventional current direction when a straight conductor is moving perpendicular to a magnetic field. So very specific conditions. So what Lenz's law allows us to do is predict which way the current is in other scenarios. So if the wire isn't straight, so maybe it's in a coil. So anything else, we can use Lenz's law for that. So that's why it's useful. So what is Lenz's law? So we can add this to our definition section of our booklets. So Lenz's law tells us that an EMF is induced in a direction so that it can oppose the change that created it. So that's what the definition of Lenz's law is. So once we've added that to our booklets, what we can do is actually see what that really means. What is Lenz's law and how do we use it? Let me give you a scenario. So what we've got here is on the right hand side we've got a diagram of this setup. So we've got a magnet at the top, it's dropped through a tube and that has coils wrapped around it. So you can see it has these 5 coils and these coils are connected in series, so they're connected one to each other. And across all of them is this voltmeter. Okay, so in a circuit diagram form, it looks like what you can see on the left. You can see we've got these 5 coils in series with this voltmeter. So the first question is, as the magnet falls, will a current be induced? Why not? So the answer to that question is no. And the reason is because a voltmeter has near infinite resistance. In reality, we're talking hundreds of mega ohms. So we're talking sort of millions or billions of ohms of resistance. So very, very high resistance. So even if you induce an EMF, there's not going to be a current. So and you can see that using V equals IR. If you have R, which is infinite, it doesn't matter what V is, you're not going to get a current being induced. Okay, so that's first of all, so we're not measuring the current here, we're measuring the EMF that's going to be induced. Okay, so that's first. Okay, so how will the voltmeter reading be different as the magnet falls? Well, the key is that gravity is going to be acting on our magnet. So essentially the magnet is going to be getting faster and faster and faster. That's the first key thing. So the faster the magnet is going, the more field lines are going to cut through the coils per second. So that means we expect, using Faraday's law, to induce a larger EMF. So that's the first thing we're expecting to see. We're expecting to see that the voltmeter reading should increase with each coil that the magnet passes through. That's the first thing. So that's just using content from the previous video. What's the actual EMF going to look like, and how is Lenz's law going to make that prediction? So the graph is actually going to look like this, and this is why we're going to need Lenz's law to explain what's going on. So in terms of things you can see, so first of all, you can see as we go along here, the EMF is clearly increasing. So this is coil 1, this is coil 2, this is coil 3, and in between where it's not going through a coil, we can see we're not getting any EMF being induced. So we've got the EMF going up, and the other thing you'll notice is that the time period is getting shorter. So initially it was pretty big, and we can see that our time period where we're actually inducing EMF is getting shorter because the magnet is traveling faster, so therefore it takes a smaller time to pass through. So let's just annotate that onto our diagram. So magnet is faster, so time in coil is shorter. Okay, so that's the explanation for what's going on there, but we've already explained why the peak is getting bigger. Okay, so let's explore why the graph goes up, goes back to 0, and then goes down again, because that's where we need Lenz's law. I'm going to look at 3 different scenarios. The scenario where the magnet is above the coil, the scenario where the magnet is below the coil, and the scenario where the magnet is in the middle of the coil to explain the shape of the graph. So, when it's above it, I told you that the EMF is induced in such a way as to oppose the change that's created it. That's Lenz's law. So if this coil is going to oppose this magnet, the top of the coil is going to need to become a south pole, and the bottom is going to become a north pole. Why? Well, the south and the south pole will now repel each other. So we're going to get a repel in there. That's how it will oppose the motion that's creating it, by inducing a magnetic pole. So this is us stating Lenz's law. An EMF is induced to oppose the motion of the magnet. So if we're inducing an EMF, we are going to be producing these poles here. That will allow it to oppose the magnet. So the north pole is induced at the bottom, the south pole is induced at the top to repel the incoming magnet. And a key rule here that we need to know is you must always produce both poles. You can't just produce a south pole and nothing else. You can't produce a north pole and nothing else. You have to make a north and a south pole together. Okay? So that's why if the top is a south pole, the bottom has to be a north pole. So that's at the top. Let's now look when the magnet is below the coil. So when it's below, how are we going to oppose the motion of the magnet? Well, we would need this to be a south pole here, so that we now have them attracting each other. So that's how the coil is going to oppose the motion of the magnet, which must mean we're producing a north pole at the top. So let's put that into words. So a south pole is induced at the bottom to attract the magnet. That will oppose the motion of the magnet and essentially have a force acting against its motion. And since you'll notice that the poles have now reversed, that must mean the current in the coil must have reversed. That's how we'll produce the coils at the opposite ends. Because originally, in the first scenario, what we had was a south pole at the top and a north. And now what we've got is this north and a south. So we must have changed the EMF and therefore the current direction at some point. So how do we know the point where the EMF or current changes direction? What we're going to think about now is the scenario where the magnet is in the middle of the coil. So from the middle of the coil, we must produce a south pole at the top, because that will attract back the north pole at the top. But we must also produce a south pole at the bottom, because that's going to have a repelling force on the magnet. So essentially what we've done is we've tried to induce a south pole at both ends. But we can't do that. As I said, you have to produce two poles together. So what happens is those two cancel each other out and you produce no EMF and no current and no poles in the coil. And so that's why the graph goes through this sort of wave section here. So that's where we're at this point on the graph here. So this is when it was above, this is when it's in the middle, this is when it's below, and then you get these sections either side where it's not in the coil. So that's explaining the shape of the graph using Lenz's law and the fact that the EMF is always induced to oppose the motion of the magnet.